Okay, guys. Today, I'm going to talk about scheduling operations among processes. Scheduling operations among processes are quite important and widely studied topic. There will be questions in our final exam or in other exams that you will attend. There will be questions related to this topic in doctoral qualification exams. So it's kind of very well established area of operating systems topic. And it's also interesting for recent issues in operating systems and computation, distributed computation, cloud computing, and all the contemporary issues, relevant issues, are highly related to scheduling, process scheduling algorithms in here. We will be discussing about basic concepts, criteria for the scheduling, different criteria, and scheduling algorithms, performance of scheduling algorithms. We will discuss about what thread scheduling is. We will discuss multiple processor scheduling, real-time scheduling, and algorithm evaluation. At the same time, slides have that these are from the book. Slides have some simple examples from well-known common operating systems. So the idea is to reason for CPU scheduling. Why do we need CPU scheduling, and how do we do CPU scheduling? Why do we have different algorithms, and how different algorithms perform? Is there a best algorithm, and so on? And different operating systems might have different scheduling algorithms implementation. Okay. Now, in a given CPU, you execute some form of program, and that program requires input and output, either to user or to external environment. User is also external environment. So a program waits for input and output, like please enter number 1. So those kind of things are considered as input-output waiting. And then it runs again. So it runs for input and output and runs again. So generally, any program has CPU and I/O parts. When I/O is executed, CPU becomes idle. Okay. So when you have P1, P2, P3 different processes, distribution of CPU bursts among different P's. I won't say equally, but properly is the main problem of the scheduling. So how do we distribute CPU bursts so that the throughput of the system, in one case, throughput of the system is increased. So we will have the best available throughput for the CPU. In the last lecture, I discussed about this little bit, but this today I put images to make it more understandable. So in a machine shop, which is a computer, an operating system, you may have a CPU, and you may have multiple tasks, processes. So each process will be executed by a CPU. Here there is another CPU, I think, but I consider it as a one person. So only one CPU is available in this image. Probably this is the second CPU. So hands of the second CPU is there. But my picture shows single CPU now. So dual CPUs require dual person. They can work on different tasks independently at the same time. If one CPU will work on different P1, P2, P3, because he is only one person, he works on one process for a while, then switches to another task. So we call it as time sharing. I hope you watched the video named as Time Sharing by Fernando Corbato. So a little bit from this, little bit from that, little bit from that, and then at the end, it looks like simultaneous execution to the user. If you have any questions, let me know. I have the chat window open in front of me, so if you write anything, I can see it. As we say, this is the dual core version of the operation. When we are scheduling operations, each operation can be represented by fixing a car. So there is a priority issue. This priority issue is well understood if you attach different priorities to different tasks. So each task has a user. If that user has a priority, higher priority, then his task will be executed first. So in this picture, obviously, police car will be repaired earlier than the other one because they have other business to go. So it will be fixed earlier. Again, when we are doing scheduling, we have different types of tasks. Some of the tasks are short, some of the tasks are long. So we need to consider the fact that when two customer arrives, meaning that two user, one is tire change, the other one is engine. So customer A and customer B has these tasks, and customer A has 5 minutes job, engine fixes 5 hours job. And if A arrives before B, will you say that A was first Probably yes, because it was tire fix. But if A is A, then B, that's okay. But B and then A, you have a problem, because since it's going to take 5 hours to fix the car of B, tire change will wait for 5 hours rather than 5 minutes. So in the first case, total waiting time of 2 people, average waiting time of 2 people, tire change will wait for 5 minutes, right? Engine fix will wait for how much? 305 minutes. At the end, they have 310 minutes total waiting and 2 customers. So total waiting, average waiting will be 155 minutes on the average. However, also the customer satisfaction is good because tire will be fixed very, very early. But if you execute, B comes little bit before A. So if you say first come and first serve will be, I mean, you will take the number and wait for your number. I don't care. And that will be, first customer will be waiting for 305 minutes. Second customer will be waiting for 300 minutes. And total waiting time will be 605 minutes. And average waiting time will be 302 minutes. So total waiting, average waiting time will be increased significantly, and tire change customer will be unhappy. Do you understand?
Yes, it's clear.
Okay.
Yes.
So okay.
It's the same you said before. There's a video about time sharing. Actually,
Yes.
it's the same. It's the same.
Yes.
Some priority.
Exactly. So there are some, as I said, there are some long tasks and short tasks. So your algorithm should keep a proper balance of scheduling criteria. However, when engine comes, can you estimate that it's gonna take 5 hours? Maybe not. For some tasks, you can estimate how long it is going to take. But for other tasks, there are surprises. So due to surprises, you cannot predict future. So you can either say first come, first serve, or you can look at the task briefly and make an estimation based on rule. For example, if it is a paint job, you say it's going to take 2 days. If it's a tire thing, it's going to take 1 hour. If it's an engine thing, it's going to take 2 days or whatever. So you can make estimations based on rules. How those rules are generated? They are generated based on visible property of the problem, properties of the tasks. So like size of the code, for example, or how big memory is occupied by the code. So it might be related, or you can, for example, if the task is a barber task, hair cutting, instead of auto mechanics, Same example can be given with haircut salons. You may have more than one barber. You may have more than one customers. Each customer will take certain amount of time. They will have their haircut and go. And some customers ask for a lot of things. So they are complicated customers. So next time the customer comes, the barber knows his haircut is going to take a long time because last time it was a terrible experience. So there can be an estimation based on the previous experiences. So if the process in the operating system, if the process is running frequently, so you can estimate the previous experience, how long it did take in the previous run to estimate the next run. So that can be another rule to estimate size of the task for scheduling purposes. And just like the barber shop, processes are waiting to get done in front of the shop. So there are queues. In English, we call it queue. In the American English, it is line. But in operating systems, it is both queue in American and US English. So if we are talking about computer science, it is universally queue rather than line. This is line, but that's for cars. So most of the tasks are easy, whether it's a barber, whether it's a mechanic, or if it's a tailor, if it is a CPU. Most of the things are around here. So some of them, only few of them are longer. Very long ones are very rare. Very short ones are also very rare. So most of them are around some average value. That is statistical value. That's not predetermined, statistical value. So it happens that way. So how long you are going to, how long you spend for fixing a car or making a haircut of a person, it's a statistical issue. It depends and it is measured after you perform it. So in order to give priorities, in order to control which one is going to be done first and next, and then how long we are going to allow CPU to run for that task, is determined by scheduler and dispatcher. There are two entities. Those are programs of the operating system. There are criteria. Here are the criteria. There is a short-term scheduler. Short-term scheduler selects processes from the waiting line. So in the shop, you have task 1, task 2, task 3, task 4. These are corresponding to cars, and you have a CPU here. So short-term scheduler determines how long it's going to spend time on this, how long it's to spend time on this, how long it's going to spend time on others. So we determine based on their sizes, based on their previous performances, but CPU rotates. And furthermore, you have P5, P6, P7 waiting outside. These are waiting outside to be taken into the operation. That is called as scheduling related to these things are called as long-term scheduling. These are scheduling among running processes are called as short-term scheduling. There can be more than one scheduling algorithm and multiple queues. In here, for example, the guy will work on P1, P2, P3, P4, and again P1, P2, P3, and so on. Assume that he is or she is a car mechanic. But in the shop, you may have Audi line and VW line. You may have 2 cars in Audi, 2 cars in the VW, and you have the guy. So what is the problem here? So you have 2 different lines. In that you can introduce 2 different lines. So in this one, Audi has more priority than VW. That means this guy is going to spend more time on P1 and P2 than P3 and P4. So you may have more than one line. Even for the single CPU, you can have more than one CPU, of course. But for the single CPU, you can have different lines. So one line gets more attention than the other line because those cars are more expensive, etc. So those processes can be more important, more demanding than others. So you give more priority to those lines. So different lines, different queues can be introduced. Furthermore, there is a preemption. In the preemption, before explaining that, this guy works on car P1 and does some job. There are 2 possibilities. He can finish or he works too much on P1. So dispatcher says, leave that car and work on some time on P2. P1 is enough. You worked on P1 is enough because the customer, the owner of the P2 is waiting outside looking at you. So although the car is in the shop, nobody is working on the car. So the customer is seeing that, which corresponds to interactivity of the application. So let's have some interactivity and go to the P2 and work on some work for some time on P2. Dispatcher tells that. So in order to tell that, preemption can be done. And scheduling decisions must be performed. Preemption means going to the person and pulling him from working. So he does not stop working by himself. We tell them to stop and move. That is what we call preemption. Otherwise, if there is an I/O, if he orders a part, or if the task is finished, or if the task requires some waiting, then he can stop working on the car and move to another car by himself. If he doesn't, after some time, we will preempt him. So this is the scheduler. Scheduler schedules who comes first, which car needs to get attention from which usta, which mechanic, and so on. So which CPU is going to run which process and how long. But there is a dispatcher. Dispatcher gives the control of the CPU to the process selected by the short-term scheduler. So he operates the control. He operates the scheduling, switching from one car to another, switching from one task to another task, switching to user mode and switching to supervisor mode, jumping to proper location in the user program to restart that program. So starting, stopping, and controlling the context is controlled by dispatcher. And dispatcher is actually something like this. So more intimate with the mechanic. So he can control what's going to go and what was left. So context will be also controlled rather than general scheduling. And as you dispatch the mechanic from one car to another, there is a walking time. There is an adaptation time. So what was being done should be remembered from some cards. Maybe you write context to the cards and leave that on each car. So when mechanic comes back, looks at the card, we call it as process control block in operating systems, and looks at the card. And so program counter was there, so registers were like that, so İngiliz anahtarı were at that place. So that was the last thing I did, so let's start again. So he has to remember certain things, and also he has to move from one car to another car. It takes time, so that is what we call dispatch latency. That's it. This guy is dispatcher. Any questions so far? Okay.
Hocam bir şey sorabilir miyim?
Tabii sorabilirsin.
Şimdi az önce verdiğiniz örnekte araba tamircisinin dışarıda bekleyen arabaların yani proseslerin fazla olması durumunda, yani oraya bir kaynak ayırıyoruz sonuçta, o işleme gireceklerin sırasında bir boyutu veya bir uzunluğu olmalı. Yani bu uzunluğun dışında olanlar yani olursa yani burada bir şey mi oluyor? Onlar zaten kuyruğa giremediği için işleme alınmıyor mu? Ya da
normalde öyle bir şey var diyemeyiz. Mesela desktop'ta tıklıyorsun uygulamaya, öbürüne de tıklıyorsun, öbürüne de tıklıyorsun, öbürüne de tıklıyorsun. Nereye kadar tıklayabilirsin? Teoride limitsiz.
Evet.
Ama pratikte tabii pratikte caddenin sonuna kadar falandır yani.
Anladım. Peki bir de hocam yani priority'sine göre, yani önceliklerine göre birden fazla sırada olabilir demiştiniz. Bu sıralardan dolayı starvation olma durumu söz konusu olabilir mi?
Olur tabii. Hep polis, vali, kaymakam gelirse sen vatandaş bekler yani.
Bekleriz değil mi?
Evet. Hatta sözünü kestim. kitapta bir örnek var. 1972'de makineyi kapattıklarında MIT'de 1965'ten kalma bir proses hala bekliyormuş. Yani
Çok eski.
scheduling. Evet.
Evet. Bir de hocam mesela az önce anlattığınız doğru mu anladım bilmiyorum ama yani kullanıcıların daha doğrusu proseslerin bekleme durumu yani daha doğrusu hesaplanan miktar yani süresi ayrılan süre aşağı yukarı sadece tahmin edilebilir süre
Evet.
ayrılıyor değil mi? Yani
Evet.
gelecek
Evet.
bilinmediği
Evet.
için
Evet.
çünkü araya
Evet.
başka işler girme olasılığı hep var ve daha da
Hep var.
artabilen işler
Hep var. Bir
olabilir.
de bir program, şimdi bazı programlar mesela bir paketin gönderilmesi, HTML diyelim, web sayfasında paket göndereceksin.
Evet.
O tarz programlar lineer programlar. Ama bazı programların içinde döngü var. O döngünün içinde de condition'lar var. O condition'ların ne olacağını bilemezsin, tahmin edemezsin. Her seferinde farklı. O yüzden ancak estimation yapabilirsin. Zaten o biraz sonra daha geleceğim. O önemli bir konu.
Tamam. Tamamdır. Sağ olun hocam. Teşekkürler.
Well, scheduling criteria is interesting one. Depending on what you are doing. For example, are we operating a barber shop? Are we operating a supermarket? Are we operating a car mechanic service? So depending on what we are doing as a business, of course, I am talking about operating systems, but depending on the nature of the operation, for example, is it a web server? Is it a firewall? Is it a database server? Is it an application server? Is it an interactive system? So is it a cellular phone? So it depends on what you are doing, what kind of programs are running on the platform. So that is highly related to selection criteria, and the following different criteria are available in theory and also in practice. Those are as follows. One is the CPU utilization. You may say that I am paying for this mechanics big money, so my main concern is don't letting them to stand without any task. So keep them busy. That is one thing. Because if you assign one car per one mechanic, and if the car requires certain amount of waiting because you need to wait for some glue to fix, then it means the mechanic is going to wait idling. So he is going to wait for input and output or some sleep time. I don't want that. So my main concern can be CPU utilization. Do something, doesn't matter how you are doing. Second, it is also interesting in barber shops or mechanic shops, throughput. How many tasks are completed? Number of processes that complete their execution. So would probably short tasks are favored because short ones are executed and quickly finished. That is what throughput oriented decisions are made. Third, turnaround time. So turnaround time is kind of customer perspective criteria. How long you are going to wait after you submit your job. On the average, of course. So our previous example with the tire change and the engine change, tire change and engine, if you do tire change first, then turnaround time, average turnaround time will be better. Obviously, you cannot increase the turnaround time for the engine change because it's going to take long, but you can improve others by eliminating additional weight. The other thing is the waiting time. This is also interesting. That's interesting. And also this is interesting for interactive services. So how long it's going to wait before anything is being done? You come to the mechanic shop. They say, okay, sit. Nothing happens. Your car stays there. So you don't like it. So you don't like it. What happens, what needs to happen is someone should take your car inside, open the hood, and leave it. In that case, you will think that your car is being fixed. So some initial instructions, certain instructions can be executed so that your you are in the CPU, started execution, not finished yet, but waiting time is finished. So waiting time in that case is reduced. Response time means giving some output to user. So it is similar to waiting time. Some output is given to user so that the user thinks that the program is running fast. That trick is done by several applications. Certain outputs are given to users, so user is expected to fill that output or click on that output. Since it is going to take time on the user side, additional time will be obtained. It is like if it's going to take long, take the car inside and send the person to the customer saying that, can you fill this form? Actually, that form is not necessary. That form was not necessary about the car or whatever, about the mileage. But just for, or maybe it is necessary, but not that necessary at that time. But some output from the mechanic shop makes customer happy. So makes he or she believe that the operation is running. Operation is running fast. Even you can call some tea for him or her. So giving some tea or coffee to the customer is another nice example of giving some response to the process, to the waiting process. These utilization and waiting time and turnaround time. Turnaround means finishing time. Waiting time means before starting time. Response time is giving some output to user. So optimizations and making decisions based on that. And throughput is number of processes that completes per second or per millisecond or per hour. Okay, that's it. So that is done by either targeting maximum CPU utilization or maximum throughput or minimum turnaround time or minimum waiting time or minimum response time. So these are all obvious after I explained, I think. Do you have any questions? Please let me know. So here's an example. In this example, you have 3 different tasks. That could be barber, tailor, car mechanic, or operating system. The first task takes this amount of time, let's say milliseconds. Second task takes 3 milliseconds. Third task takes 3 milliseconds. They arrive in the order P1, P2, P3 at the same time, but they arrive in order. So this is the door in the morning. So they arrive at the same time, but there is an order still. They may not arrive at the same time. We will talk about that later in the next example. So if we say first come first serve, sorry, yani sıranı bekle kind of approach. P1 is going to take 24. P2 is going to take 3. P3 is going to take 3 milliseconds. So total waiting time, each waiting time will be how much waiting time for P1? 0. How much waiting time for P2? 24. How much waiting for P3? 27. Do you understand? I think yes. If it is no, please let me know, because not all of you can say yes. So waiting time, total waiting time, I mean, sum them up. So 24 plus 27 and 0 over 3, because I am interested in the average, is 17 milliseconds. How about turnaround time? In turnaround time, what's turnaround time for P1? 24. P2? 27. P3? 30. So average turnaround time is 27 milliseconds. So although you have short tasks, with this scheduling criteria, average turnaround time is increased. So customer satisfaction is highly reduced. How are you going to fix this? If they arrive in other order,
Dispatcher.
Yeah, dispatcher will say after this time, dispatcher, if it is a preemptive, dispatcher will say let's work on P2 because their job is short. So you can leave P1 for a while. Or if it is not a preemptive operating system, you can reorder those priorities, you can implement P2 and P3 first, then P1. That is called as, maybe some of you will remember, shortest job first scheduling. You implement the shortest one available at the time. So that may cause starvation if there are a lot of things coming, but that can be overcome by a process called aging. I make analogy with that using angry customers. So a customer can wait, but as you wait, your temper increases slowly. So if you are waiting too much, you are angry, then your priority changes. You go to the scheduler and complain. They call the dispatchers, indicating that what was the problem with this car, etc. So your priority can be increased. If there is no mechanism for that, there might be starvation. Her gelen geçiyor abi şeklinde bir duruma düşebilirsin yani. So if the operation is on the other way around, P2, P1, P2, P3, P1, average waiting time for P1 is 6. That's 6 is here. Waiting time for P2 is 0. P3 is 3. So average waiting time for the system is 3. That's very nice. So 3 versus 17. So turnaround time of P2 is 3. Turnaround time of P3 is 6. Turnaround time of P1 is 30. So total will be 39. And average turnaround time is 13 milliseconds. 13 milliseconds with respect to 27 milliseconds. So it's much better. This strategy eliminates the convoy effect. This strategy eliminates the convoy effect, which is short processes behind long processes causes problems. Yeah. And if we consider CPU bound and many IO bound processes, this is the case. IOs wait. You click on things on screen, that's IO. Nothing happens because antivirus or FTP download is working at the background. So your computer does not respond. That means bad scheduling. That's first come, first serve. So sıranı bekle scheduling algorithm. Second one is the shortest job first scheduling. Of course, you can choose among the jobs that are available at the time. If 3 customers, customer 2, if 3 customers, this is 3, customers arrive at time 0, you can choose among those, shortest one. Another customer comes at time 3 or time 4. You can decide whether you are going to switch to the new task or select from the previous one in certain times. If it is preemptive, you check the algorithm periodically if there is a new customer, or if it is a simple shop, once you finish one of the tasks, you include the new customer to the set. So first you have 3, then you finish one of them, the shortest one. Then the next customer comes. Now it is 3 again. So each time you are going to start new task. You evaluate, are there any new customers? So that is one technique. So get the shortest one. Get the shortest one. But again, there might be starvation. The difficulty is knowing the length of the next CPU request. Sometimes even you can ask to the user, is it a high priority thing or low priority thing? How long it's going to take? How much you want to give priority? If it's an system software, the software developer can decide on it. This is what shortest job first example is. You have 6, 8, 7, 3 coming at the same time. So when you are if they come at the same time, obviously this will be executed first, this will be executed second, this will be third, and this will be fourth. So P4, P1, P3, and P2. That's the execution time. Average waiting time is actually first waiting time. P1's waiting time is 0. P2's waiting time is 9. P3's waiting time is 9. P4's waiting time is 0. So the average waiting time will be 7. When we are going to talk about turnaround time, P1's turnaround time is 9. P2 turnaround time is 24. 9, 24. P3 turnaround time is 16. P4's turnaround time is 3. So total what? Total 40, 49, 3, 52. 52 over 4 is equal to 30. Do you understand? Probably yes. Please let me know if you have questions.
Hocam burada sıralamayı kim yapıyor sürekli? Yani dispatcher mı yapmış oluyor?
Yes, short term scheduler.
Okay, sorry.
So the difference between dispatcher and schedulers are actually not clear. So let's say scheduler together.
Okay, thanks.
How I'm going to estimate? We can only estimate based on the previous visits. A barber shop is a very good example. If you are going to consume time of the barber a lot, it is always the case, usually. Therefore, previous visit is a good indicator. On the other hand, if you only consider previous visit, you don't consider the previous of the previous visit. You should also consider previous of the previous, or previous of the previous of the previous. But recent ones should count more. So the scientists achieved an algorithm indicating with the Tn. Oops, what happened? Tn minus 1, Tn minus 2, Tn minus 3, and T0. So you can always have previous first, but you don't want to calculate Tn plus Tn minus 1 plus Tn minus 2, 2 plus Tn minus 3 plus over n. This is difficult to calculate, and latest one has the same weight. Obviously, you can give some weight like 5 times Tn, 4 times Tn minus 1, 3 times Tn, 2 times Tn minus 3. So you can do something like that, but it is not easy. So what they do is Tn plus 1 is actually alpha times Tn. No, actually, one. This is the idea. That's the formula. 1 minus alpha. I was wrong. So if it depends on the alpha value. If alpha value is 0, Tn minus 1, Tn plus 1 is actually Tn. If alpha is 1, Tn minus 1, n plus 1, that's here, is Tn. Minus, right? Yeah, okay. There is tau n. That's tau n. Yeah. That's tau n. That was my mistake. So you either decide between depending on the very previous one or depending on previous calculations. This part didn't come out. Tau n plus 1 is equal to tau n minus tau n. Yeah. Okay, I fixed it. Normally, when alpha is 0.5, tau n plus 1 is equal to tau n minus, no, that's, is that minus? Yeah. Point 0.5. Oh, yeah. tau n minus 0.5 tau n minus 1. This gives you half contribution from tau n, another half contribution of tau n minus 1. Actually, tau n minus 1 is connected with the same formula to tau n minus 2. Tau n minus 2 is connected to same formula with tau n minus 3. Okay. Let's move to example. This calculation, this is tau n, this one. And these are Tn's. T0 is 6, T1 is 4, 6, 4, and 13. Okay, these are T's, and these are tau values. First, it is calculated, it was 10. At the beginning, it was 10. Let's say that. Next, 6 plus 10 is with alpha is 0.5. 6 plus 10 is 16 over 2. That's 8. Then 8 plus 6. No, 8 plus 4 here. 8 plus 4, 12 over 2. It is 6. 6 is here. Then it is 6 again. 6 plus 6. Again 6. 6 plus 4 means 10. 10 over 2, 5. Then it is 13. 5 plus 13 is 18. 18 over 2 is 9. 9 is here. So its next estimation is here. After 9, you have another 13. 9 plus 13 is equal to 22. So the estimation will be 11. The output is still 13. So 11 and 13 gives you 24 over 2. It is 12. So it is a kind of running average. It is running average, but the problem is this is actually plus. It's a running average, and it is affected from the previous values. It stores the history of the values, but it is mostly affected. Half of them is affected from the previous value. Another half of the values are affected from the previous value, and those are also affected from their previous values. So it's an asymptotic effect of previous values where recent ones count more. So it's a good prediction algorithm based on recent results. Do you want to give a break? Okay, let's give a 5 minutes break. And Okey arkadaşlar, geldim. This is our formula. Scheduling algorithm is executed whenever one task is finished. So scheduling algorithm is executed at these points. You can decide at those points, decide. Why am I doing that? Because arrival times are different. Since arrival times are different, for example, at time of P0, only one process is arrived in the morning. Therefore, P1 is about to run. But after P1 is finished, you can decide again. It could be preemptive or non-preemptive.
Sir, we can't see the slides. Sorry.
Anybody else?
I said, yeah, we can't see the slides.
Because I am connected as a client as well. I am seeing my slides in the client.
Okay.
How about other people?
I can see.
Oh my God. Okay.
Yeah, Veli, go in and out once, so
Okay.
that it can
Okay,
reset.
sir. I will do it. Thanks.
So it can be preemptive or non-preemptive. When these decisions are done after one task completes, that is non-preemptive. When those decisions are performed when another task arrives, it can be preemptive. Preemptive means you can leave a task and start a newcomer task and go back to the previous task later. So it is kind of starting task switching. So this is preemptive. The example drawing is preemptive. I am drawing non-preemptive one first. P1 arrival 0, so burst time is 8. 0, 8, P1. But when time 8 is P1 arrived here, and P2 is arrived here, P3 is arrived here, P4 is arrived here. They're all arrived before time 3. So when we reach time 8, they are already available. So if we choose shortest one, P2 will be executed. And well, how long it is? 4, right? 8 plus 4, 12. Then P4 is executed. 5 plus 12, 17. Correct me if I'm wrong. And the longest one will be executed lastly. 26. Right? What is the waiting time for each process? P1 will wait for P3. P1 is going to wait no time. P2 is going to wait how much? Tell me.
7.
Yes, that's correct. 7 because arrival time is 1. That is important. P3 is going to wait for about 17 minus 2, 15. So this minus coming time. And P4 is going to wait for about
9.
9, yes. So average waiting time will be 31 over 4. It is 7.75. I think so, yes. So average waiting time, if it is non-preemptive, 7.75. But if it is preemptive, that is the case. P1 is executed, and at time 1, some other person comes in, and we make another decision. We make decision so that the remaining time of P1 is at this time, at time 0 is 7, but the remaining time of P2 is 4. So we compare 7 and 4, and we decide that P2 is shorter. So we execute P2. Some part of the P1 is executed. How much? 1 duration. Then P2 is executed. At time 2, P3 comes. When P3 comes, 9 versus 7 versus 9 versus 7 versus, what's the other one? The new one. 3 is compared. So once we do that comparison, what am I going to execute? I am going
P4.
to continue. Yeah. Because here is the coming point of P3. At this time, I don't switch to P4. Yet P2 is shorter. So I keep going. Then P4 comes. Burst time is 5. When that burst time is 5, I compare 9, 7, which are the remaining ones. And P2 is executed how long? About 3 times. So it is now 2. My P4 is 5. So when I compare, I still run P2. So I keep executing P2. Then I finish P2 and looked at P4, P2, and P1. No, this is not P1. P1 is this one. P4, P1, and P3. P4, P1, P3. I choose among them. And I start executing P4 because this is the smallest one after 2. This is already finished. So P4 is executed. Since there is nobody coming again, I don't execute comparison. So P4 is executed. Then once P4 finishes, I make execution. I make decision between 9 and 7. 7 is shorter, so I execute P1. I finish P1 and then I finish P3. So the total execution time, total waiting time will be 6.5 in this one. Average waiting time. So total waiting time will be 26 and average waiting time will be 26 over 4, 6.5. So this is interesting. Shortest remaining time. Abi şunun 5 dakika zamanı kaldı. Bunu bitireyim de ondan sonra öbürüne başlayayım şeklinde bir durum. So on top of these, there are priorities. Some integer number can be associated with the process. CPU is allocated to highest priority. Usually high priorities are indicated with lower integer numbers. So if you have priority 0, that means you have the highest priority. If you have the priority, if it's an 8-bit number, 255, that means you have the lowest priority. So in between, this is high priority, this is low priority. That is usually the case. In some other applications, like in Windows, you have two-dimensional priority. One is the system priority, one is the kernel priority. Each process has two kinds of priority values, and scheduling is done based on two different priority values. When we are using priority values, there are two main strategies. One is the preemptive, the other one is non-preemptive. If it is non-preemptive, once you start executing a task, you cannot go back. You have to finish it. But with the preemptive one, just like we did previously, you can stop executing one and switch executing to the next one and do the first one later. So shortest job, first priority scheduling, it is actually a priority scheduling where shortest job has the highest priority. So SJF is actually priority and determined by length. If the length is short, you have higher priority. The one problem is the starvation. Always higher priority numbers comes in front of you. Emniyet şeridinden gelen araçlar gibi. Herkesin priority'si var. Ben bir türlü gidemiyorum. So the solution is aging. So your temper is increasing. You get angry. And as time progresses, your priority also increased. And with the algorithm, then sometime later, your priority becomes enough so that your task is executed. Here you have multiple priority execution example. You have different priority values for different processes. Each of them has different priorities. So high priorities are executed. P2 is executed first because P2 has higher priority. P5 is executed then because it has the next priority number. P1 is executed then. It's the next priority number. P3 is executed and P4 is executed. The average waiting time is this. If the priorities were the same, for example, you have 4 and 4. When you have 4 and 4, then you will choose a second algorithm. You will favor for the short process or first come first serve. It's a decision. It is up to you who designed the operating system. When you have preemption is good. So idea is, let me not order tasks until they finish. Let me do certain amount from each of them continuously. So it is called round robin. In the round robin, there is a notion called time quantum. Let's say it is 10. So when you have P1, P2, P3, P4, etc., you execute 10 milliseconds from each and continue to the other. 10 milliseconds from each and continue to the other. That gives higher interactivity for the processes and more customer satisfaction, more output from applications, although they don't finish, but they act like they are working. So customer keeps happy. Task switching, number of task switching is increased, going from one to another is increased, but overall waiting time can be improved and overall throughput can be improved. Let's see one example. When the quantum is very large, let's say work 10 hours, then switch to the other car. So that is equal to first in, first out. If I say work 5 minutes on one car, then switch to another car. So 5 minutes is very short. Why it is short? Because there is a switching time. Switching time is 1 minute. So 20% of the time is spent by going from one car to another car. Therefore, the time quantum should be comparably bigger than switching time. That is one idea. So if the time quantum is not higher than switching time, the overhead of switching becomes so significant. Here is an example with the previous problem, the first problem, with the time quantum equals to 4. 4 items, 4 elements of time, you work P1. So 4 done, 20 remaining. Then you have to switch. Switch to what? First in, first out, P2. Execute that for 4 quantum, but unfortunately it finishes at time 3 because its length is 3. So at time 7, you are back to scheduler because car is finished. So the next one in the queue, in the ready queue, is P3. Then you execute that, another 3-1. Although you have time up to 4, but it is also finished. Now you are back, P1. You execute scheduler algorithm with a timer interrupt. You execute scheduler algorithm. There is no other process coming, going. Keep going. Another execution. Keep going. Another execution. Keep going because there are no other processes waiting. And so on. So these quantums are executed one after other. After 5 quantums, this 20 is also finished. Turnaround time can be can be longer than shortest jump first, but quantum is more interactive. So interaction, the response is much better with the round robin approach. That's the beauty of round robin scheduling with quantum values. If the quantum value is like 30, the algorithm will be, when Q is 30, algorithm becomes to first in, first out, because 30 has nothing to do with these numbers. It's too big. So when the quantum is big, number of context switch becomes very small or zero. As quantum number decreases, number of context switches increase. If the quantum number is too much, there are many context switches. So that is an interesting fact of round robin scheduling with preemptive capability. Preemption. Turnaround time changes with the quantum size. So when you increase time quantum, it doesn't always go up. Sometimes it can go down. So depending on how it fits into time quantums, average turnaround time may change. So it may not, it is not directly related to the size of the time quantum. It can go up and down, but generally it goes up when you increase the quantum. When you increase the quantum, yes. In this example, you have P16, P2 3, P3 1, and P4 7 as the example. As a rule of thumb, if we have 80% of CPU bursts that are shorter than quantum, then we are on the safe side. That's what Silberschat's book says. One queue is not sometimes enough. You may have more than one queue. Just like the queues in car inspection stations, you may have more than one queue. One queue is for certain priorities, and if you are waiting long enough, one queue to another queue. If you are on that queue a certain period of time, then you are transferred to the next queue. Switching between queues is performed by schedulers. So for the tasks like background tasks, antivirus checking tasks, background tasks, they can run at the background with lower priorities. But for the interactive tasks, they can run in the foreground with round robin scheduling, so they will be more responsive to user interface. Multi-level feedback queue, multi-level queue is therefore is a very good idea. When you have ability to move between queues, depending on the conditions, depending on the developing conditions, then we call it as multi-level feedback queue. So queue operations are readjusted based on the feedback taken from the process execution. This is what is an example of multi-level queue. you have system processes, interactive processes, editing processes, batch processes, and other processes. So with the highest priority, more round robin, and this is first come, first serve. So this is also round robin. Depending on the, this may be shortest remaining job first. This is again, that they can have different algorithms on different queues. And CPU spends switching, CPU does switching between these queues. The feedback queue means a process can move between the various queues. You can go up and down depending on the aging and priority change algorithm. You can change priority algorithm, therefore starvation is eliminated and more just distribution can be obtained. This is an example of multi-level feedback queue with multiple sizes of time quantums. You have faster queue here with time quantum 8. You have slower queue with time quantum 16. And you have first come, first serve, the latest lazy queue. So you first enter time quantum 8. It's fast. If it finishes, no problem. If it doesn't finish, second queue is switched. Second queue is switched. If the 16 quantum time is not enough to complete, that means 24. Then that means you are a long process and you work a little bit, so there is some intensity obtained. So let's move you to the first come first serve task. You are going to repair your engine. So let's leave you with the other long tasks. That is one idea. Multi-level feedback. And also, you can move back to other queues depending on the aging algorithm. You can move back to higher priority queues. I skipped the topic of threads. Threads are similar to processes, but they are more lightweight. These lightweight threads are also scheduled, but instead of switching the whole process control block, are switched based on their smaller set of parameters. So switching between kernels takes less, let's say, takes less switching time. Which threads have higher priority, which threads have lower priority is determined by the programmer, by the system designer. Sometimes you have processes and system operating system executes them by different threads. Each of them has corresponding thread in the operating system. In some other operating systems, for example, P1, P2, these may be run by different threads, different system threads. So this thread is responsible from, this system thread is responsible from executing two different user process threads. These are implemented in Solaris operating system. So system level threads and user level threads are somewhat different in Unix-like operating systems. These are also important issues when you are doing virtualization, because like Kubernetes or other virtualization container, Docker container architectures, the threads and the processes in your application are translated to system level threads, and those threads are run independently. So it is like a simulation, but complete simulation will be very slow. So therefore, instead of complete simulation, one-to-one or one-to-many matching of threads, corresponding threads, delegating application threads to container threads is performed for faster execution of container architecture. It's not complete simulation. POSIX threads are one example. POSIX threads, OS, Linux, and Mac OS X allows POSIX threads, although limited. There is a scope system, process contention scope, many-to-one and many-to-many models, as I said, are available. Let's move. Sometimes we have multiple processors. When we have multiple processors, scheduling becomes an interesting issue. You may have identical processors, you may have non-identical processors arranged in a symmetrical way or asymmetrical way. In an asymmetrical way, each of them has same set of priorities. In the asymmetric one, there is a master-slave relationship. We call asymmetric multiprocessing when you have a master-slave approach. If we don't, we call it as symmetric multiprocessing. And some process P1 is running on CPU, certain CPU. We say there is a processor affinity existing between P1 and CPU N. So each process has affinity for processor on which it's currently running. Therefore, switching P1 to another process is a costly operation. When you are doing scheduling, you should consider time slices, right? Regular P1, P2, P3, P4, plus the cost of switching one process to another processor, to another core also must be calculated. The cost must be calculated. So you decide whether to wait for another round or switch that process to another core or processor. That's a decision should be made by the scheduler again. So multiprocessor scheduler should decide considering processor affinity as well. There are different variations, soft affinity and hard affinity. In the hard affinity, it has to work on certain processor. In the soft affinity, it is better to work on the same processor. Sometimes different processors have different properties. So scheduling with multiple processors and multiple cores are not an easy task. Depends on the architecture. One example here about the affinity. So this system executes P1. This system executes P2. This CPU has more relations with P1 is because the P1 is residing in the memory 1. So this CPU is running P1. This CPU is running P2. If you are going to move P1 up here, so this access becomes slower. Therefore, it is better to run P1 on this machine due to throughput considerations. This is an example for the affinity problem with distributed architecture. When you have multiple processors or multiple machines, or it can be loosely coupled or tightly coupled in the symmetric approach, you need to have load balancing, periodically check load on each processor, and if something is going bad, you can redistribute the tasks so that overall throughput is balanced. And if the processor is idle, you can pull information from others. You can pull tasks from other processors so that again the load will be balanced. So you can actually think of it as like multiple shops. Shop 1, shop 2, shop 3. There are cars here, too many cars here, one car here, and no car here. And there is a mechanic guy here, another mechanic guy here, another mechanic guy here. So although these are different shops, they have some kind of agreement. So if you have a lot of things here, you move these tasks to other processors, other nodes, I would say, so that these can finish these two tasks faster. Overall throughput becomes better. That is what migration of tasks between processor farms is. And again, affinity is important in order to do that. So you move a car which is easy to move. A difficult to move car or task should stay in the same place. So you also keep track of that measure. You may have one CPU and multi-cores. So multiple processor cores on the same chip. What is the difference between multiple processors and multiple cores? When you have multiple cores, some parts are missing than having multiple processors. sometimes, and also since they are on the same chip, the clock speed of communication between cores is improved. They can share certain buses inside the chip for fast data transfer between cores. They can also share memory, so memory can be accessed inside the chip. So it's like a cache. They can access the cache memory much faster compared to the case when they are different processors on the same logic board. It consumes less power than having multiple processors. Multiple threads per core is also implemented in many places. They take advantage of memory conflict so that if one process is waiting for memory, another one can execute. So if one core is executing two threads, thread 1 and thread 2, if this thread is waiting for a certain part of the memory, thread 1 can continue. Why thread 2 is waiting for the memory? Because that area can be used for the other core at a particular time. Although different cores can access to memory together, they cannot access to same locations at the same time. So they have to wait for each other to access certain pieces of certain blocks. Certain blocks of memories can be accessed. C1, C2. C1 can access these. C2 can access these. C2 can also access this. C1 can also access this. So this is shared. But multiple threads means if this one is waiting to read something from the memory, another thread, T1 is here, T2 is here. T2 will wait, but T1 can continue. Yes, that's correct. So this is what I said actually. You have compute cycles, memory wait cycles, compute memory, and then another thread can work when there is a memory waiting going on for another part of the memory for another processes. So different threads for the same core has a lot of advantages. Also for the single core, it is meaningful, but with the multi-core approach, having more threads than one per core has more significant advantage because cores can conflict for certain parts of the memory. Then if there is a conflict, let the core run a non-conflicting thread for that time. This is what is given as an example. Lastly, real-time scheduling is an interesting topic. Typically, we have soft real-time and hard real-time systems. In the hard real-time systems, there are deadlines. In the soft real-time systems, we just say fast. Soft real-time systems does not guarantee any time, but they are fast enough to finish the task. In this hard real-time systems, there is a pre-computation by the scheduler, and the scheduler says, okay, I can do it, and it does. If it can't, it should abort the processing, and it should inform the operating system saying that it's not going to happen. This can be used in industrial control signal processing, where time limit is critical for making decisions, like robotics, for example. Hard real-time systems are necessary, or engine management control. For interactive things or virtual reality kind of, when the user is involved, soft real-time systems are sufficient. Both soft real-time systems and hard real-time systems compute the scheduling when there is a timer interrupt. So when one task is running, the timer interrupt comes. What kind of timer interrupt or another interrupt is happening? So you do operations, you execute saving the registers, and interrupt service routine is executed. Interrupt service routine makes the scheduling decisions, and then task 2 is started after executing interrupt service routine. I think this is what I did. So in the real-time systems, there are events and responses. Something happens and I have to respond it in a maximum amount of time. That amount of time should be limited because that event can happen again, just like rotating an engine or rotating some, or taking picture, coming picture from the camera. So response interval is limited. When the event happens, there is some interrupt processing time, and dispatch scheduling time, and at this time, process execution. This could be longer, of course. This part can be longer, but the total size is limited. I mean, determined. Maximum value is determined so that another event can be freely processed without any problem. I think we are good for this week. If you have any questions, let me know now. Okay, I am stopping the recording.
Hocam
Evet.